Hello students. In this video, I'll explain about stereochemical aspects of nucleophilic substitution reactions. This is a very important topic from CBSE point of view as well as from competitive exam point of view. See, I told you about SN2 and SN1 mechanism in the previous video. In SN2 mechanism, there is inversion of configuration. In SN1 mechanism, racemization of the product takes place. Now, these two things can be explained, can be understood on the basis of stereochemistry of the reaction. Now, under this stereochemical aspects, we'll consider 6 to 7 small topics, and there will be a lot of terminology involved. First term is plane polarized light, PPL, plane polarized light. You know, white light is made up of 7 wavelengths, Vipure. Even if we consider monochromatic light, that is light which is made up of single wavelength, radiation will have its vibration in all possible planes perpendicular to it, the direction of its propagation. Means what? Look here. Let us say radiation, any light is moving in this direction. This is moving in the form of, this is traveling in the form of waves. These waves can be in this plane, can be in this plane, can be in this plane. So these waves can vibrate in all possible planes perpendicular to the direction of propagation in which this radiation is traveling. Now, if these vibrations are somehow adjusted in a single plane only, then this is called PPL. So what is PPL? PPL is that radiation, that light whose vibrations have been adjusted in a single plane. And this is done by passing the radiation through a special type of prism, which is called Nicol prism. NICOL, Nicol prism. And Nicol is nothing but it's a special crystalline form of calcium carbonate, simple compound. Second topic is optical activity. Now look here. This is a tube. You can see this is a tube. There's an instrument called polarimeter. This polarimeter has a tube, and this, let us imagine, this is the tube of that instrument, polarimeter tube. In this polarimeter, solution of an organic compound is filled. Through this solution of organic compound taken in the polarimeter tube, PPL is passed. Let us say vibrations of PPL are adjusted in this plane. PPL is passed through the solution of organic compound taken in the tube of polarimeter, and this radiation comes out from this side. When it emerges out, look here, incident in this plane, when it comes out, if plane of PPL is rotated towards right hand side or towards left hand side, if plane of PPL is rotated by this compound taken in polarimeter tube, then we'll say that this compound is optically active. And the phenomenon of rotation of plane of PPL by a compound is called optical activity. Now, there are two possibilities. Plane of PPL is rotated by the compound in the clock direction. Clock is called right hand side, or anti-clock direction, that is left hand side. If plane of PPL is rotated towards right hand side, that is clock in the clock direction, then this compound is called dextrorotatory. Dextrorotatory. And this dextrorotatory compound is represented by using the prefix D or plus. D should be small d because capital D will have some other meaning. Small d or plus written within brackets followed by hyphen. So if the compound rotates plane of PPL towards right hand side, that is clock direction, then this is represented by using D or plus before the name of the compound. So if I write D2-butanol, it means dextrorotatory 2-butanol. If I write plus 2-butanol, it means I'm trying to say it is dextrorotatory 2-butanol. Similarly, if the plane of PPL is rotated towards left hand side, that is towards anti-clock direction, then this is called LAEVO, levorotatory compound, and this is represented by using the prefix L or minus before the name of the organic compound. And as I told you, instrument used to measure angle of rotation of plane of PPL by any compound, that is called polarimeter. Now coming to third topic in this category, third topic is molecular asymmetry, chirality, and anisomerism. I'll write because spellings may be confusing for you. Molecular asymmetry, chirality, and anisomerism. Now, look at this model. This is carbon atom. 4 balls of 4 different colors represent 4 different atoms or groups of atoms attached to this carbon atom. So that carbon, which is bonded to 4 different atoms or groups of atoms, that is called chiral carbon, CHIRAL. This is called chiral carbon, also called chiral center, also called asymmetric carbon, also called asymmetric center, and also called stereo center. So these are 5 terms used for this type of carbon, which is attached to 4 different atoms or groups of atoms. I'll repeat: chiral carbon, chiral center, asymmetric carbon, asymmetric center, or stereo center. Now, if you want to give the example of any compound which contains chiral center, what you have to do is you don't have to remember any example. Write a carbon atom and attach any 4 atoms or groups of atoms to this. You can attach 4 different halogen atoms. That will become a chiral center. You can attach hydrogen and deuterium. If you attach different isotopes, then also this will be a chiral center. So attach any 4 different atoms or groups of atoms to a carbon atom, that becomes the example of a chiral carbon atom. Now, if molecule has a chiral center and if it is non-superimposable on its mirror image, then it is called asymmetric or dissymmetric or chiral molecule. First, let me show you the model. I'll tell you again. Look at these 2 models. Look at them carefully. They are mirror image models, mirror image of each other. Imagine there is a mirror in between the 2 and they are mirror image molecules. This is the chiral center. If you try to superimpose one model on the other, it will not be superimposable. Same color superimposes, but these are different. You can try the way you want. These are non-superimposable mirror image molecules, and these non-superimposable mirror image molecules are called asymmetric molecules, also called dissymmetric molecules, also called chiral molecules, CHIRAL, chiral molecules. And this non-superimposability of mirror image molecules is called chirality. Remember, if there is only one chiral center in the molecule, like in this case, it will always be non-superimposable on its mirror image. It will always be optically active. It will always be optically active. Out of these two mirror image models, two mirror image molecules with one chiral center, one will be dextrorotatory and the other will be equally levorotatory. These are called optical isomers. These are also called enantiomers of each other. And the phenomenon of existence of such optical isomers or enantiomers is called optical isomerism or also called enantiomerism. Remember, chemically, enantiomers represent the same compound, but arrangement of atoms or groups of atoms in 3D is different. Enantiomers have similar physical properties and chemical properties, except the direction of rotation of plane of PPL by them. Direction of rotation of plane of PPL by them will be opposite. Rest every property of enantiomers will be same. Now, those molecules which have which are mirror image molecules, but they are superimposable on each other. They are called achiral molecules or they are called symmetric molecules and they are optically inactive. I'll show you with the help of a model. Now you can see these are same. These are mirror image of each other. This is not chiral center. Although they are mirror image, but they are superimposable. You can see all color balls, they superimpose on each other. And this type of superimposable molecule, mirror image molecules, but superimposable, they are called achiral or symmetric molecules, and they are optically inactive. Coming to next topic, fourth topic in this category, racemic mixture. I told you about racemic mixture in SN1 mechanism also. See, racemic mixture is nothing but mixture which contains equal quantities of dextro and levo forms of the same compound. It means equal quantities of dextro 2-butanol plus levo 2-butanol. So equal quantities of dextro and levo forms of the same compound when mixed together, then the mixture is called racemic mixture. And as I said earlier, process of formation is called racemization. I told you dextro is represented by using D or plus. Levo is represented by using L or minus before the name of the compound. Racemic mixture is represented by using DL or plus minus before the name of the compound. If I write DL or plus minus 2-butanol, it means I want to say racemic mixture of 2-butanol. Remember, every molecule of racemic mixture is optically active, but mixture on the whole is optically inactive. Every molecule of the racemic mixture tries to rotate the plane of PPL, but that optical rotation of one molecule is cancelled by some other neighboring molecule which will try to rotate the plane of PPL in the opposite direction. So every individual molecule is optically active, but mixture on the whole is optically inactive. This is called external compensation. Externally rotation by one molecule is compensated by rotation by the other molecule. Now, next topic in this category is retention of configuration. Retention of configuration means configuration of the reactant and the product formed is same. In SN2, there is inversion. In SN1, there is racemization. Retention has not come so far. In retention of configuration, configuration of the reactant and configuration of the product formed after NSR is same. It does not change. And this is possible only if during the nucleophilic substitution reaction, bond of the stereo center, bond of the chiral center is not broken, then only configuration will not change. I'll take an example. If we consider plus means dextrorotatory, 1-chloro-2-methyl butane. This I'm writing in rough. This is 1-chloro-2-methyl butane. This is the chiral center. I'll write a little bigger. This is 1-chloro-2-methyl butane. This is the chiral center. Now I'll represent in 3D. This is chiral center. Halogen. This is halogen attached to CH2. This is bonded to hydrogen, methyl and ethyl. This is plus means dextrorotatory. So this is dextrorotatory 1-chloro-2-methyl butane. Let us say it reacts with aqueous NaOH. When reaction with aqueous NaOH takes place, this bond will break. Chlorine will be replaced by OH. It means during the reaction, bond of the stereo center will not break. Bond of the stereo center will not break. Therefore, configuration of the product will be same as the configuration of reactant. This is called retention of configuration. So product will be called plus 2-methyl-2-butanol. Reactant was plus, product is also plus. This is retention of configuration. Next topic in this category is inversion of configuration. Inversion of configuration, I told you in SN2 mechanism in detail. Now, in inversion of configuration, product has opposite configuration compared to the configuration of reactant. But it does not mean that if the reactant is dextrorotatory, product will be levorotatory. It does not mean that. I'll take an example. Let us say we consider dextrorotatory 2-bromobutane. This is chiral center. Bromine, hydrogen, methyl, and ethyl. If this undergoes reaction by SN2 mechanism, hydroxide ions will attack from the backside, and this will lead to the formation of product. And this product will have an inverted configuration. Now, this does not mean that if this reactant is dextrorotatory, then the product is levorotatory. Now, there is confusion here. In case you are writing about this in board exam, CBSE, then you will say that dextrorotatory reactant gives levorotatory product, because there is inversion of configuration. But as far as your competitive exams are concerned, it will be slightly different. There is inversion of configuration, but remember, reactant is different from the product. This compound is different, whereas product obtained is different. Now, whether this product formed will be dextrorotatory or levorotatory, that will depend on priority order of substituents attached to chiral center. There is a priority order of all the substituents attached to the chiral center, which will decide whether the product will be dextrorotatory or levorotatory. So as far as your competitive exams are concerned, we will only say that during SN2 mechanism, inversion of configuration takes place, and the product formed may be dextro or levorotatory depending on priority order of substituents attached to the chiral center. Now coming to the last topic in this category, that is racemization. Partly I told you about racemization. This takes place in SN1 mechanism. Step 1, carbon halogen bond breaks heterolytically, forms carbonium ion. Carbonium ion is attacked by nucleophile from either side and leads to formation of 50% product molecules which have the same configuration as reactant, 50% product molecules which have an inverted configuration compared to the reactant. Now here, I'll just take an example and then explain. I'm taking the example of 3-bromo-3-methyl hexane. You can see this is the chiral center attached to bromine, hydrogen, ethyl, and methyl. If you remember, SN1 mechanism is followed by tertiary alkyl halides. Therefore, I've taken the example of a tertiary alkyl halide. Now, this I'll represent as a 3D structure. Hydrogen, ethyl, and propyl. Sorry. Hydrogen, ethyl, propyl. चलो ठीक है, it's okay. If we consider dextro and levorotatory 3-bromo-3-methyl hexane, let us say this is dextrorotatory, it means levorotatory will be this H ethyl propyl. When these two undergo reaction with aqueous NaOH by SN1 mechanism, in step 1, bromine will leave as bromide ion and both will lead to the formation of same type of carbonium ion. Whether the reactant is dextrorotatory or this is levorotatory, carbonium ion formed by both of them will be similar. In step 2 of the reaction mechanism, this is attacked by the nucleophile, that is hydroxide ion from aqueous NaOH. Step 2. Now this carbonium ion can be attacked from either side. It means 50% product molecules will have the configuration like this. 50% product molecules will have the configuration like this. It means a racemic mixture will be formed. How do we write the product? I'll rub and write. I'm writing product here. This is racemic mixture formed. Right? So this is called racemization. Reactant was optically active. Product is also optically active because there is a chiral center. 50% product molecules will be dextrorotatory, 50% product molecules will be levorotatory. So whether we start with only dextroreactant, whether we start with only the levorotatory reactant, product form will always be a racemic mixture if it is a tertiary alkyl halide and reacts by SN1 mechanism, right? So that's all about the stereochemical aspects.